of it. Here we go. I'm gonna do that, gonna put that there, and then we're all ready. And let me make sure Danielle can still see. Can you still see, kid? There we go. And make sure she can hear me because I'm muted. That's awkward. There you go, kid. All right, let's go over it. Let's see, because I want you guys to know right away, if you should be coming back in at some point this week by Friday to take it again. You can get your 0 period stamp. P.S. When is 0 period this week? Thursday, because tomorrow's an A day. All right, number 1, pop off. Let's go. What do you got? Integral of x to the 4th is? Oh, wait, you just did this. Just say it out loud. What do we got? 1/5 or x to the 5th over 5, right? Either way. Plus x cubed or 3x cubed over 3, which would just reduce, right? X cubed minus 5x squared over 2 or 5/2 x squared, either way, plus 7x, because it's a constant, plus c.
Oh my gosh.
No.
Whew. And there's partial credit all over the place. Retake it. That's okay. But hey, did you double check your answer to see if it derived to be the same thing?
Yes.
You could have double checked every single one of your answers and see if it was right or wrong. But it could be x to the 5th over 5. It could be 5x squared over 2. Rocco.
That's
Yeah.
what I was enough.
Yeah, totally okay if you did that.
Oh, I think I put a plus.
But wait. Does mine work? The 5 comes down. It's gone. X to the 4th. Check it. The 3 comes down. 3x squared. Check it. The 2 comes down. Negative 5x. Check it. 7, 0. How are we doing? How are we doing with deriving to check? I'm not saying you got it 100% right, but do you guys get you can derive your answer and see if it works or not, right? Okay. Number 2, did you know your trig rules? Woo-hoo-hoo! Negative cosine of x minus 3 cotangent of x. The derivative of tangent is secant squared, so the derivative of cotangent is negative cosecant squared. No. Don't worry, because there were points for getting the basic one, and there were points for getting the harder one, right? And there are like lots of points. It's out of 10 points. But you can get like partial credit all over. What do we got? 1, 2, 3, 4, 5, 6, 7, 8. Plus C is 9. And I'll probably just give you a free point 10. There you go. Sound good?
I got 6 right.
10.
I put plus 3 times.
I'm not going to integrate this one yet, right?
No, keep going.
Oh, maybe this should be the point for just rewriting it. I don't know. We'll see.
Yeah.
But 4,
Yeah,
the rewriting. Okay, that's a point. Plus x to the 2/3. How was the rewriting?
Oh, let's go.
How was the rewriting? Did you get that point?
Right, first one wrong.
Wait, 2/3? Oh, I guess
I don't think about the rewriting. No, because 7 was like 4.
Equals.
I got 7.
It's too early.
Maybe you missed the try.
Gotta add 1 and divide by. Gotta add 3 over 3 and divide by, which is the same thing as. You could have just left it here. You could stick it to the man, and I would take it. But you could have also made this negative 2 over x squared plus 3/5, or any variation thereof. 5/3 plus. 1, 2, 3, 4, 5, 6, 7, 8. The plus c's are 9. The rewriting is 10. There you go. 10 points. You can retake it anytime you want. Nutrition's a little rough sometimes, but even then, you can just grab me a blank sheet of paper and I will give you 3 similar questions. Like right now?
Sure.
How about the end of class? Does that sound good? If we're working on something? But are we okay?
Can I just add the plus C?
Oh, you didn't hear my hints?
I want that.
What were my hints?
Just go back.
Hold on. I'm going to do this like for the next few quizzes and tests. So when I said make sure you see, what was I hinting at?
No, I guess
Whether you need to add anything at the end, because if you don't see, if you're missing something, it might be very sad. That was a hint. Okay. Well, I mean, I was trying the plus C's. You were. Is that all you missed though? Was just the plus C?
Yes.
What? That's still a 9 out of 10. Maybe we should make some bonus in here. Hold on.
Actually, I kind of messed up the second one a little.
Can I find a place to have 11 points? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
You can make each plus C.
Each plus C a point. Oh, but then
No, hold on.
Yeah.
No.
it's great for his score. Can anybody find another place? Oh, I could do the signs for the trig.
Nice.
Oh no.
So that'd be
Let's not do that either.
1, 2, 3, 4, 5,
Oh, yeah, I
6,
put
7,
Not
Oh,
8, 9, 10, 11. I could almost have that be a bonus point.
Please, you put the D out.
No, it's okay. I'll read it.
Plus C if you.
If you put the number before the entire question, you should get an extra point.
Oh,
Go
if you
one.
wrote
You put 1, 2, 3.
Yeah, that's a good idea.
Yeah.
If you wrote your name, it's worth a point. Okay, that's good.
I love those.
Yeah, got it. Got it.
So I just freaking chickened out. Put a question mark there.
I'll find a way to put 11 points in, but still retake it because you get a bonus in the test quiz category is never a bad idea. P.S. If you retake it and it's lower, I'm not going to give you the lower score. I just want you to be studying and working and trying to get a better score. Is that cool? Okay, all retakes for this must be done by the end of the week. Okay, here we go. Section 4.2. I have WebAssign open and ready for us to look at if we... Oh, why didn't it open? Well, I thought I had it open. I mean, it's over there kind of waiting for me to have it open. I just can't record all the different names. Question. Question. Did I or did I not post a video that you could have seen examples on this homework assignment in Google Classroom? Hovan saying yes, so yes I did. Cool. I'm not going to take super long though. I'm not going to take super long then to do a left, a right, a midpoint. Ooh, why is that blank? Oh, I think because I was going to go to WebAssign. Okay, I'm not going to take super long to do a left, a right, a midpoint, and then we're going to go to WebAssign. There are a couple other things, but I might just leave that for another day. So, here we go. What's the big idea of section 4.2? Area is a thing. Area is the second big problem in calculus. Area is what integration answers. Not the only thing it answers, but it is one question that it answers. And so with area, we are going to use rectangles most of the time. We also use trapezoids a little later, but rectangles, we're going to use rectangles most of the time because the geometry is easy. It's base times height. The base being how far apart the little x's are for a certain partition that a rectangle comes up out of. Height being where it stops, which is always something to do with where it hits the function, where it hits the f of x axis. So, to get these examples in our notes, my clue, you guys can write down this if you want to. First of all, this is the same exact example for the next 3 pages. Okay, so go ahead and write down that example. We're going to do it 3 different ways. We're going to do it with left endpoints, then right endpoints, and then midpoints. But we're solving this exact same example all 3 different pages, just we're doing it 3 different ways. Why? Because calculus, the AP exam, is very precise whether they want a right Riemann sum, a left Riemann sum, a midpoint Riemann sum approximation is what they call it. Or as I know Josh saw in homework and maybe some others of you did as well, sometimes they ask for upper or lower, but then you kind of have to figure out if that's left or right based on the nature of the curve. So for each subinterval, we start by knowing the function. We start, if you want to make a picture, you totally can. It probably would be helpful. We take the beginning and ending interval and say, hey, kind of like a sign chart. We say, hey, kind of like a sign chart. Let's think about that 0 to 3. It makes it way easier to think about it up here. And guys, if we're splitting a distance of 3, right? 3 minus 0. If we're splitting a distance of 3 into 3 subintervals, what am I going by? And if you can't do that in your head, there's always a formula, and the formula says, actually let me write it in black as far as the general formula from the page before. Then I'll write it in red for this specific example. To find the base, which is how thin or how thick the rectangles are, I'm going to take my b minus a all over n. Maybe a better way of putting this is just writing the word base, because B is also the end of the interval. So what's 3 minus 0 divided by 3, cool kids? What does that mean? That means I am going by ones. So 0 to 1 is going to make one rectangle. It's going to come up out. 1 to 2 is going to make another rectangle. And 2 to 3 is going to make another one. These are my partitions. This is how I'm cutting up my graph. So if I come down here and if I see there's my 0 and here's my 3, I'm going to go ahead and make a rectangle there, make a rectangle there, make a rectangle there. However, I need to somehow give it height. So this is my base. These are the bottoms of my rectangles. The question is, how high do they go? Josh Yang, I know you've done some practice on this. The question, how do you know where to make the rectangle stop if it says left approximation?
Well, if you're doing yours at like the first rectangle on the right, it would be at the 0 because that's the left bound. Wait, sorry.
Oh, at the 0, at the 0? Got it. So he's saying come up at the 0 and hit the curve. And he's saying that's making the height of my rectangle. Because I think he's also looking over here and seeing, hey, 0 is the far left of that interval. And he's exactly right. What is the far left of that interval? It's 0, so I'm going to come up and hit at 0. Guess what? F of 0, whatever that is, we'll talk about in a second, is the height of the first rectangle. And then I need another rectangle, so then I take the next partition. Here was the first partition, and that first partition landed at 0. So from here to here, I'm going to use the 0. From 2 to 1, I'm going to use 1. From 3 to 2, I'm going to use 2. Those are my 3 different rectangles. So I hit at 0, I hit at 1, I pop out. And then I hit at 2, and I pop out. Not perfectly in front of the board because I'm trying to go up from the side, so all my rectangles are slanty. Lo siento. But what's the idea? The idea is I have f of 0 for the first height of the rectangle, I have f of 1 for the second height, and I have f of 2 for the third height. And if I was trying to add all these areas together, I could say A1, A2, A3 for my 3 different areas. But remember, in calculus, we like to be efficient. We like to find shortcuts that are accurate. Not just like sneaky ones that sometimes work, but ones that always work. So check it. If I was to do base times height, I haven't even thought about my function yet. I need to. But do you guys see that my left, some people would call it, I think, Josh, did you see this in homework at all? LRAM, did you see that at all? Is that a thing that ever showed up?
Not to my.
No, okay, then let's not worry about it. It's a left Riemann approximation. What is that? Left Riemann. Area. I forget what all the letters are for. But it's basically saying you're coming from the left and you're doing a Riemann approximation. I don't remember what the M is for. But some people do LRAM. I could also do something like A sub L as far as the area coming from the left. And then check it, guys. If all of the bases are the same, I could factor that out. And if I factor that out, all I have to worry about, since I'm adding everything, is just doing my f of 0 plus f of 1 plus f of 2. Now, in this example, that's not too hard, because what is my function from up here again? Isn't it 9 minus x squared? So if we wanted to, we could have figured out what each of these are as far as, hey, what is f of 0? Take a quick time out and say f of 0 is 9 minus 0 squared, or 9. What is f of 1? 9 minus 1 squared, which is 8. What is f of 2? 9 minus 2 squared, which is 5. Are we okay with all those numbers? So I can do my 9 plus my 8 plus my 5 times my 1. And I get my left Riemann approximation to be 17 and 5 is 22. Double check my math, but I'm pretty sure. Yeah? Okay. Why am I not just going to call this a left approximation because I'm hitting on the left, I'm hitting the curve at the left of the rectangle? But why am I also going to call this an upper sum or an upper approximation? Why am I going to call it an upper? Do you notice what the rectangles are doing? Yeah. Check it. I'm trying to approximate this nice little curvy area that has no geometry formula to match it. This is not a circle. It's not a rectangle. It's not a triangle. I'm trying to approximate that. But what kind of approximation is it going to be, guys, if these rectangles are popping out over the curve? It's going to be an over approximation. Does that make sense? So it's above, it's an over approximation. WebAssign is going to call it upper because it's an over approximation. You can see it both ways. It over approximates. It's on the higher end. But that's coming from the left. Now, have your calculators out if you have them in class. We're not going to use them quite yet, but we are going to use them soon. Have your calculators out. I'm showing you that some of these can be done by hand for sure. But have your calculator out because what's the highest, those of you that have looked at homework, what's the highest n gets in homework? Is it like 8 or 10? Fitting in?
I said
8? Okay. Yeah, I was thinking 8 might be the highest. In years past, I think it's been 10. This could get really tedious if you had to do 8 different calculations, right? You're like, ugh. Especially if the function wasn't quite so basic as 9 minus x squared. So we're going to look at our calculator in just a second, but hold on. Hold on. Those of you that have already started doing this, looked at the examples, this is just review, making sure you have it solid and making sure you have something in your notes for when it's like a month or two from now and you've forgotten everything that you could remember, right? It's the exact same example. You don't have to write it again, but please write that we're doing a right-hand approximation this time, just so we can all get the idea of a right-hand approximation. I know in this one it's basic, but in other ones it's not, so please see that there is a way to figure out your base by just thinking about what are my two different endpoints, what distance is between them, and you're cutting them in how many different pieces. Then you can have your little breakdown. Not mental, you know, just, anyway. Coming back. I wouldn't have even thought about that like 5 years ago. Okay, if I'm coming from the right this time, over here I was coming from the left. Coming from the left, I chose 0, I chose 1, I chose 2, because I think Josh said it well. He was like, hey, on that interval, 0 is the left of that interval, or 1 is the left of that interval, or 2 is the left of that interval. So check it. If I was to do the same thing with this guy, I wouldn't be choosing those same numbers. Oh, I'll use black as midpoint. Ding. I'll use yellow. On this little subinterval, if I have a rectangle popping up out of it, I need the one on the right for a right approximation. I need the one on the right for the right approximation. I need the one on the right for the right approximation. I'm going to be using these other guys, 1 and 2 and 3. And what does that look like down here? Once again, trying to approximate this guy. But this time for my 0, 1, 2, and 3. When I pop up in rectangles, the question is, where do I hit? I'm not going to go up and hit at 0. This time I'm going to go up and hit at 1, and then that determines the height of my rectangle. So if I was to be growing this, it's like as soon as it hits the curve, stop. Okay, cool. That's the right-hand approximation in this example. Go up at 2 and hit. Go up at 3. Ah! 3 doesn't go up at all. I know, but I still have to use it. That's how the approximation method works. So I'm going to be using f of 1 for the height of this guy, f of 2 for the height of this guy, and f of 3 for the height of this guy, which is awkward in the picture, but in the math it's not awkward at all. Because if I just wasn't really thinking about it, A1, A2, A3. Just trying to add together some rectangles. I have my base, base, base. It's all about what do I got? And then my f of 1, f of 2, f of 3. I'm just pretending like we had no idea what these were, that we didn't just solve for some of these. Remember, just plug into that original function that we have up here. So 9 minus 1 squared, PEMDAS, do the squared first, and then the minus. There are rules that tell you what order to go. That's why it's 8. 9 minus 2 squared, do the squared first, that's why I get the 5. 9 minus 3 squared, oh, that's awkward, isn't that 0? But my right area approximation, I could pull out all of those different GCFs. What I would have inside would just be my f of 1 plus f of 2 plus f of 3. Once again, we'll look at how to use our calculator efficiently if we're allowed to, but we're plugging in the 8 and the 5 and the 0. And why, after all this work, when I get 13, why am I going to call this a lower sum? Why is this a lower sum? This guy was an upper sum. Why is this guy going to be a lower sum? Yeah, exactly. It's seriously that basic. And I know it might not seem like it, but if you look over here, this is an under approximate. This under approximates the actual area. Now, can I show you why, or how you could tell this without even knowing or having a picture? You could see this because my function right here, this little f of x, it actually has nothing to do with its concavity, and it has everything to do with my f is decreasing. Has everything to do with your f, your function is decreasing. So if you're using the value that is further down on the number line, its value, its y value is lower. If the function is decreasing, this guy's y value is lower than that guy's y value. So because my function is decreasing, something that we saw in chapter 3a, 3b, if we can figure out a function is decreasing, who cares about the graph? We don't care about the graph. We'll know what's over, what's under based on whether the function is increasing or decreasing. If the function was increasing, it would be switched. If we were on the other side, the left would be the under and the right would be the over. The picture would illustrate that. But it's all to do with what is the function doing. If it's decreasing, then choosing a later y value would, yeah, make it lower. If it's increasing, choosing a later y value would make it higher. How are we doing? We're adding together rectangles. Sarah?
Did you do the times 1 in front of everything because of the base?
Yes. I did that because of the base. Good. And if this was, I mean, in homework, you're going to see bases that are different. I think one of your bases, isn't it like 1/8 or pi over 8 or something like that? I think one of your bases is like an awkward pi over 8. So then if it was pi over 8 was like my little increments, that's just what I would be multiplying in front. But this one, it was a 1 because I ended up just going by ones to get my 3 rectangles in this space. Is that cool? So the last one, ready? What if we had midpoint? Same problem, you don't need to rewrite it, we're just doing it a different way. P.S. This is how the AP can get you. Because your calculator might be able to find you the exact answer, and they're like, we're not looking for the exact. We wanted an approximation, and we wanted a specific one. The answers will be different for anything that's curved, anything that's not linear. So just getting you into the habit, once again, we're looking between 0 to 3. I know we've already done it, but we're getting the habit down. So what are our bases? Our bases are going to be, well, think, you're taking the distance between 0 to 3, you're cutting it into 3 subintervals because they said so, which means I'm going by ones, which is why I'm doing the 0, 1, 2, and 3. All of this is for the purpose of approximating. But this time we're approximating with midpoints. So in this interval, I'm not looking at the left, I'm not looking at 0, I'm not looking at the right, I'm not looking at 1. I'm looking at the midpoint, which is going to be, we can see this one at 0.5. If you can't see it, you can always, like, say you couldn't see that it's 1.5. It is 1.5, but say you couldn't see that, remember, you can always find it at midpoint using the average idea of 2 plus 1 divided by 2. That's 3 over 2, or 1.5. If you're like, ooh, midpoints could get rough, they totally could. You can always use the average idea for the midpoint. And then in between 2 and 3, what's the midpoint? 2.5. So if I was coming over here for my A1, A2, A3, I'm just trying to illustrate to you guys you don't need the picture. We know our base from that little baby formula over there. Just subtract the distance, divide it up into however many pieces they say. I know my base for each and every one of these is going to be 1. Which is why I'm pulling out that GCF of 1, since they're all same, since they're equally spaced, this is my midpoint approximation. But what about everybody else? Well, I'm going to use my f of. Have you guys gotten into that habit yet? Even though the numbers are different, you're still just stealing the special x values, right? So what am I going to plug in? It's not 0, 1, 2. It's not 3, 2, 1. Instead it's... Yeah, exactly. 0.5. And then? Exactly. And then? Exactly. And if you needed to, you could take these over back to the function. You could say, hey, who are you? 9 minus 0.5 squared. We'd have to use a calculator. Isn't that just 1/2 squared? And isn't 9 minus 1/4 the same thing as 36 minus 1/4, aka 35 1/4? I'm not saying that I'm like gonna force you to do horrible mental math and homework. I'm just letting you know you're more powerful than you think. When you get to the non-calculator portion of the AP, if they were to ever throw at you a fraction, you're not incapable. This guy, as a decimal, it would be gross, but as a fraction, I can do 3/2 squared. That's 9/4, 36/4. Remember, get that common denominator. Most of you have gotten a lot better at common denominators in calculus because you've had to with the power rule. But get that 36/4 minus 9/4. 36 minus 9, take some time, it's 27/4. 2/5 would be 5/2 squared, 2.5, right? 36 minus 25. Do a little bit of mental math on that, but I think it's 11/4. Feel free to double check me and make sure I'm not lying. 35/4, 27/4, 11/4. Anybody back me up on that mental math? 36 minus 1, 36 minus 9, 36 minus 25. I think that's good. I'd have 35/4. Which, I mean, I can just add them up, right? 30, 40, 50, 60, 68, 73. Oh, wait. 30, 50, 60. Yeah, 73, right? I think so. 73/4. But this is where it gets a little dicey. Is it an over? Is it an under? It's not exact. If it was exact, then a triangle would take that area. It's not exact. But let's go to 0.5 and let's get up there. Let's go to 1.5. Let's get up there. And let's go at 2.5. A little rough, right? Because aren't you noticing it's a little bit above and a little bit below? Sorry, a little bit below and a little bit above. And then again, it's a little bit above, it's a little bit below. Switch, a little bit below, a little bit above. Stink. Looking at the wrong thing. The rectangle. The rectangle is a little bit below and a little bit above. So you know what I do to make it a little bit clearer as to whether or not it's over or under? I pretend, what if it was just one big midpoint? What if I just did one? Because all of the approximations should behave the same as long as the function is the same concavity and the same increasing, decreasing on that whole interval. That's why I'm not doing both sides. If I was to do one midpoint, so if I was just to go to 1.5, maybe it'd be better if I did it over here in a different color, maybe something like blue, if I was to go at 1.5. Is that a little bit clearer? What do you guys think? If I just have one midpoint. Look at how much above it is. How much the function is above, and then how much the function is below. What's it look like? I agree, Victor. I think you got it. Didn't you say upper? Yeah. Yeah. It pops out more than it falls under. I think that technically has to do with concavity. That's something that we should probably keep an eye on when AP practice comes about. But I tend to just draw one big fat one, and that should show me. So one big fat left one would come up here and would pop out. Oh yeah, that's over. One big fat red one, right one, I mean that's 0, so yeah, that's definitely under. And one big fat midpoint one, remember, midpoint of the x coming up to hit the y, that's definitely more over than it is under. So it is going to be an upper, but I'm going to call this a barely upper. It's much closer than the other one was, but it's also nastier to solve. Let me get rid of this nasty stuff over here. Don't love that picture that I drew. But someone in WebAssign, find me a nasty one. Find me a nasty one for me to get ready for everybody else. But as I get that ready for everybody else, hey, we get to use our calculators sometimes, right? Open them up. Let's make sure we can use them efficiently for problems like this, because, oh, there's a great trick. Not one that you haven't seen before, but one that you might not think of seeing. Get that calculator out. I want you to get that function 9 minus x squared near y equals. Yeah, go ahead, Sarah. That's the easiest mathematical way to never get stuck. Like on this one, you might have seen it was 0.5, 1.5, 2.5, just because you're used to like measurements on rulers. But other things like with pies, it's going to be a mess. So the average way will always get you halfway, as long as you're using the two little endpoints of that little, what we call partition, that little subinterval. The average of those two will get you there. The average of those two will get you there. Because if you notice, 2 plus 1, that was 3 halves, and I used that. 3 plus 2 is 5 halves, and I'm going to use that also. Yeah, that average idea will always get you there if worse comes to worse. In your calculators, I'm having you graph 9 minus x squared. Now, let me be super honest, okay? There are programs I could give you, and I've done it in the past, that says, like, give me the function, I'll just spit it out. You can program your calculator with games, you can program your calculator with programs. There is a Riemann approximation program. I don't think I have it on this one because I've had to reset this multiple times. I think I have it on the one I use in class sometimes. But once again, calculators have gone missing over the years, so my one with all my nice programs is probably gone at this point. But there are cool programs that say like, hey, I'll do the whole thing for you. Tell me the function, tell me your n, I'll do it for you. The dilemma is the AP knows this. And so if they were to allow a calculator on an exam, they wouldn't make it nice and evenly spaced, where all of them have a GCF base. They would make them awkwardly spaced in a table, so the programs all would fall short, if that makes sense. Unless the program says, like, give me a table, and it could be programmed to do that, give me a table. But let's just say they've turned these into non-calculator problems. But for homework, etc. Okay, ready? Remember, there's an n equals 8. What does that mean? 8 rectangles. Blech. On homework. So check it. Couldn't we do these calculations by saying, since they're evenly spaced, there's my GCF of 1, right? Isn't there this cool, watch my buttons. Don't push my buttons, but watch my buttons. Ready? Alpha trace. Or go alpha F1 and go over to F4. F4. Why is this guy super cool? Because he says, I know function notation. So for the left Riemann sum, if we know our different values, check it. I can go and I can get y1 of 0, y1 of 1, y1 of 2. This was what the left guy was doing. Remember, he was starting at 0, 0, and then 1, and then 2 were those 3 ones for the left. I can do function notation. So guys, if my function were ever super, 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 super nasty, I don't have to plug it all in. I don't have to do all this calculation. I can just say, ha, 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 go. Oh, hey, it's 22. Do you remember you can also go up and copy paste? I showed you last year, doesn't mean you remember. You can do your little cursor up, up, and say, hey, I want you again. For what? How about what if the right? Ugh, I don't want to click, 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 click. Second back takes you to the beginning of the line. I'm not sure if it really saved you a lot of time. But I want to do the right one this time. 1 and 2 and 3. Woo! Wasn't it 13? Now, midpoint. Hey, do some of you ever start typing things and it overruns what you just typed? And then it really stinks? Do we remember how to get around this? Second back takes you to the beginning of the line. I want to do 0.5. If I put 0, I'm going to start overwriting. How do you stop that? Insert. Second delete. Say I want 0.5. 1 point. Second insert. 1.5. 2 point. Second insert. Come on, put your calculators to class. It's not every day. Wait, is that right? 18.25? Well, I didn't actually figure this out, but that is going to be 4 goes into 7 1 time, 33 8 times, and 1/4, 18 and a fourth. Yeah, it is. But remember, you can also always do, ready, alpha y equals the one we love for the fraction. Number 4 says I'll take a fraction to a decimal or a decimal to a fraction. Math frac, there it is. Or you could literally do math frac. That also works too. Did I lose anyone? I'm plugging into the calculator if we need to. Let me let you look at the screen for a second. I'm going to ask again if there are any questions in just a moment, but I'm looking for someone who's... No, I want to do left. No, they want me to do right. Why am I writing a little 1 to 3 over here? P.S. for those of you guys that are like, I'm good, I'm solid, awesome. Section 4.3 Jamboard is up and in your Google Drive. That's where we're going next. Yeah. Well, and like 1 and 3 is my beginning and end, right? And then n equals 8. But guys, remember, don't we have a cool little formula to say, okay, no stress, what's my base going to equal? If I'm equally spacing it, just take the distance and cut it into how many pieces? Whatever they tell me. Does that make sense? Just take the distance. 3 minus 1 is 2. Cut it into eighths. Isn't that how you go by fourths? Now, be strategic. Come on, let's be efficient. What are they telling me I'm allowed to use? Use your calculator. So if you're using your calculator, do I want fractions or do I want decimals?
Yes.
Yeah, right? So let's go by 1.25s. Sorry, 0.25s. So I'm going to have 1, then I'm going to have 1.25, then I'm going to have 1.5. Do you guys need me to write all these? I don't think so. But do we get the idea? If we cut these into all the different, there's 2, 2.25, 2.5, 2.75, cool. I'm going to have 1, 2, 3, 4. Look at the spaces. Look at the spaces. 1, 2, 3, 4, 5, 6, 7, 8. So could I, for the left, could I do A1, A2, A3? Could I do that 8 times? Yeah. What would my bases be every single time? Yeah, 1/4 or 0.25, because that's just the distance, right? It's how much is in between everybody. And Sarah, this would be one that a midpoint would be in this. I would definitely be averaging, right? 2.25 cut in half. I don't know. Go find it. Cool. But all of them, hey, be strategic. If all of them are going to have this, right? Yeah, can't I just make it a GCF and put it out in front? Gorgeous, saves so much time. So you don't even have to write all this if you understand what's going on. They're equally spaced, because I'm doing it and I'm going to make them equally spaced. All of them will have the exact same base. But what else do I need? If it's a left, if I'm trying to find the left approximation, think of your first little baby subinterval. This little rectangle is going to hit the curve at what x? The one on the left. So that means I'm going to use f of 1, right? For the next little baby subinterval, 1.25. For the next, 1.5. Now we could keep going, but we're trying to find a pattern, right? I'm not going to make this too difficult because it's not like n equals 100. If it was n equals 100, we'd be like trying to make a math formula for what's going on about how we're doing 1 plus 1/4 n. We could make a little formula and we could put it in a big old fat sigma and we could have some fun with it if we had tons of rectangles. But for right now, we only have 8. Maybe it's not that bad. Hold on, where would we stop? Guys, what would be the very last? They would cover the rest of the space. What would be the very last f value? Yeah, 2.75, nice. Once again, you don't need to write this unless this helps your brain know what we're doing. What we're just going to be doing is, let's just do f of 1, f of, no, not f of 2, f of 1.25. Now I know it's a little bit tedious, but plugging into that by hand is not going to be very much fun, but using technology is going to be great. Let me change the screen share for Danielle to be able to see. Now I can't use these exact ones, but I can use this idea. I just need to throw in my new function, right guys? My new function is 3x squared plus 3. Go delete whatever that guy is. Is this making sense? Go throw that function in. Use your GCF of 0.25. And it's going to be annoying the first time, but what's so cool when we go to do the right Riemann sum approximation? We can copy, paste, and change the numbers, right? So we're going to have 8 of these. It's not great, but it's going to work, and we have y1 of 1. You guys see me get into that trace? Alpha, go straight to the trace, y1 of 1.25. Practice, give your brain that muscle memory. You do drills in your sports to get that muscle memory. Do it in math class too. This is a great shortcut that comes in handy in lots of different ways. Well, I'll show you the other way. But it uses a Riemann sum, and you have to be a little creative with it. It's great, and it leads us into section 4.3. But still, this shortcut of how to find the y1 and how you can plug into whatever function you want, like you're getting that shortcut down so nice right now. But why am I stopping at 2.75? That's it. That ends. 2.75 is the left and it goes out and hits 3. I'm done. I don't need a picture. 2.75 is that last one. Let me just illustrate. 1.75 would also be, but there you go. You would have these guys. You would have 1, 2, 3, 4. I should have 8 different ones here, right? Feel free to double check. Let's just see if we all land in the same place. 29.0625. I'm going to do a quick, let me know if I'm wrong, because I could have definitely gotten off. I was talking while I was inputting, and that's always dangerous. You guys agreeing or disagreeing? Sarah, you got the same thing? Cool. Takes time. But what's the really cool thing when we go to do the right?
Just copy paste.
Copy paste, except what's going to be different? Well, on the right hand one, you guys good if I just go straight to the not this setup, but instead what would change? AR is still 0.25 for my base. But what's going to change is this time I have, what's my very first one? Yeah, my very first one over here would be 1.25. I'm going to hit these guys, so then check it. I'm going to hit, everything's going to stay the same, except where do I land? And what don't I have? So all you got to do is delete the y of 1. Remember how to do that? I'm going to catch up with you in just a second. Delete the y of 1. So I'm starting at 1.25. And I'm ending. You got to add in f of 3. But actually, you don't even have to change all those numbers because you just have to take out the first and say, well, it doesn't have the first one. Oops. There we go, enter. It doesn't have the, oh, are you guys still clicking? What's the shortcut? Second back button takes you to the very beginning. Second back takes you to the very beginning. Then just delete. Not clear. If you clear, then just go copy paste again. Ugh, I've got to click. No, go to the end of the line. Second. Look. Second, forward. Woo, there I am. And then just add in one more y1 of, are we learning our technology, cool kids? 35 point. Are we all in agreement?
I agree.
Victor agrees. Go team. Hold on, what's up, bud? Yeah, there is, and that's exactly where we're going next, because some of you guys are like, there has to be a shortcut. And there is. But it depends on whether or not you like it, and whether or not it makes sense, because we don't have to use it in AB. We can, but we don't have to.
Just add 0.
There are a couple slides that say, hey, what if, we're not going to do this activity because we're a little bit behind, but guys, check it. I've kind of copy and pasted it from another year. That was 8. That was 8, and 8 was tedious. Are we all in agreement? That was 8, and 8 was tedious. Do you guys see the what if at the top of the screen from last year? What if it wasn't 8? What if it was 10? What if it was 100? What if it was 1,000? I don't want to do that 1,000 times. Sigma. Check it. What if now this is actually for our original example, the n minus x squared. It's not for the one that we were just doing. But we could make it for the one that we just did. Let me change it up to make it the one that we just did. What was the one that we just did? The one that we just did was 3x squared, because I want you guys to be able to get the answers that you just got. Cool? Let's see. So what if we were doing, what's that function, guys? 3x squared plus 3? Was that it? 3x squared plus 3. And we were going between 1 and 3? Right? So then this would be 1 to 3. What would we need to change? We would need to change, this is based on n minus x squared, that old one. So we'd have to change this to be our function and our check it. How sigma works is it says, you know what, just give me, I don't want that one. Give me I equals 1 to n of f of, so we have to use our function f of x, and that's why I'm going to have to go erase all these because that was the old f of x. We have to use that function, f of x. But we're going to do f of a plus, and you saw me do that over here as far as I had the 1 plus a fourth, 1 plus 2 1/4, 1 plus 3 1/4, 1 plus 4 1/4. I was kind of doing that over here, and we'll show it over here. But your A plus your delta x sub I times n, which we were going by fourths in the screen before, and then times your delta x sub I. This is just allowing it to change, but we're doing equally spaced so it won't change. So look and see what this means for our problems. I wouldn't be spending as much time here, but A, it is a shortcut, and B, it does lead us to the limit definition of an integral, of a definite integral, which is exactly what section 4.3 is. Okay. Might need more space. I know, it's Jamboard, I can only do so many things. So I would have my 3 times, but I would need this to cycle through however many I have. So I need to do 3 times 1 plus, if I was going by 10, well, let's start with what if we were just doing this guy over here, which is going by 8. So if we were going by 8, we could do I equals 1, 2, 8. Now, I'm doing the right Riemann sum. It's the easier one to put into your function. You would need to have f of 1 plus 1/4 n times 1/4. That's all you need. But you need to make it particular to your function. So if you guys want to try your sigma, you could like take all of this addition of 8 different y whatevers, and it would be I equals 1 to 8, how many rectangles, of 3 times, my x gets replaced with 1 plus 1/4 n, or 0.25 n, squared, because that is my 3x squared, plus 3 times 1/4. Before we go looking at what changes with 10 and 100 and 1,000, will this get us the same answer of 35.0625? Let's check it. Second. Actually, isn't there alpha window? Isn't there a shortcut for sigma? I think alpha window, F2. There's a nice shortcut for sigma, or math, you can scroll. But I just do x equals because I'm a lazy bum. I is too hard to find with an alpha button. I'm going to do from 1 to 8 of my 3x squared, but 3 times 1 plus, if you guys want to use decimals, you totally can, 0.025. N, I'm saying n, we technically need it to match whatever variable we have. So in this case, it would be I, or in my calculator, it's going to be x because I'm being a lazy bum. And I don't want to go find an I button. Squared, 3, this thing squared. So this is what's going to move through my 1, 1.25, 1.5, 1.75, etc. And then plus 3. And then I need this whole thing to be times 0.25 for all my little bases. Let's double check. Ooh, scary. Hold on, I have too many parentheses. I need this little f of x to be in his own parentheses. There we go. So I have my sigma for the whole thing, and then I have my little f of whatever times there are all my different heights, all my different bases. Boom, shaka-laka-laka. What do I change if I need it to be n equals 10? 2 little baby things. Guys, would I be going by 1/4 if I had 10 different rectangles? No. If I had 10 different rectangles, what would I be going by? Well, I would need to be going by, ready, remember? I'm going 3 minus 1 all over 10. Or for 100, I'd be doing 3 minus 1 cut into hundreds. Or 3 minus 1 cut into thousands. We saw last time, the more rectangles you have, the more precise it gets. So I would need to change my little 1/4, 0.25 to 1. Isn't that 2/10? Isn't that 1/5? So I could do this whole thing, but second back to be a lazy bum. I could go to 10, but I need my math to show that I'm going to 10, meaning I'm going to be going by 0.2s this time, 1/5 instead of 1/4. And 0.2s, that would be 10 rectangles. Or if I wanted to do 100 rectangles, I could just say 100, but I need to also change my math, because now, hold on, if I'm going by 100s, 2 over 100, isn't that 0.02? 2 over 100s? So this one would be going by 0.2s. This one would be going by 0.02s. Maybe somebody could guess this would be 0.002s. My rectangles are tiny. Second insert. Using all our buttons today. Oh, I didn't make that 0.2 up above. Struggle bus. There's for 8. You guys see I didn't change the other one. It needed to be 0.2 at the end. Going by 0.2s for 10. There we go. This looks to be more convergent. And then going to 100. Don't worry. This is not something you're going to have to do like tons and tons, but it does get you to the idea of what a definite integral is. Now I'm fitting in 100 rectangles. Struggle bus. Do you see anything interesting happening with these numbers? I had 35.0625. I had 34.44. I'm going to grab pictures of these real fast before like my next entry. Are they getting bigger and bigger and bigger? Or do they seem to be getting... Huh. Does anybody remember Zeno's paradox last year and taking an infinite number of steps but having it held within a finite amount? Me going to the podium? Cutting half the distance every time, and I could do that mathematically forever, and yet that podium would never move and I would never go beyond it. The idea of convergence. Second, insert a 0. I could do this all day, cool kids. I could go to 10,000. I could go to 100,000. Do you seem to see? My calculator is literally finding 1,000 different rectangles and adding them together. Pretty cool technology. Love it. Does there seem to be convergence to a single answer here? What's it seem to be getting closer and closer and closer to? Yeah, it seems to be getting closer and closer and closer to 32, right? Excuse me. My voice is dry. Let me go block out all these guys up here because I ended up just showing them in the calculator instead, so you don't necessarily need to see all that. But what would happen if we used a very different button indeed? You ready? Important idea for section 4.3, important idea for the new one. Can you guys all go find for me? I know I've lost a lot of you. I know I've lost a lot of you. I see you on your phones. But hold on. Here's the big clincher that gets us to the next section. Do you see what's happening when I fit in 10, when I fit in 100, when I fit in 1,000? Do you notice that that area under the curve would be getting tighter and tighter and tighter and tighter in the sense of, remember yesterday I split it up more and I split it up more and I split it up more? Imagine 100 different ones or 1,000 different ones. They're tiny. How tiny? I can tell you in this example, they're like 0.002 apart from each other. Like, ugh, that'd be annoying to do by hand. Calculator does it all for me. That's so cool, but check it, guys. What if I was to use, ready? Alpha window, cool shortcut. Do you see the little integral guy? Function integrate and derive, take a ddx of, take an integral of, I'm going to do number 4. But it's asking for numbers on your quiz today. There were no numbers. But wait, are there numbers in my example? And the answer is yes. I'm going between 1 and 3. I'm going between 1 and 3. I'm trying to figure out the area under the curve of 3x squared plus 3 dx Want to make a guess as to what you think that might be? No? Oh, you should have. Could have bet money on it. It's 32! I'm not saying you should bet. But you could have. 32! Don't bet in the Super Bowl. You might lose. Coming back.
You want the Bengals to win so bad. That is 9 squares available.
Well, now that I lost you all.
$100.
Okay. Don't literally be making bets in front of me when I just told you not to. Shush.
Joe Shiesty.
You ready? You ready? You ready? Where does this 32 come from? Besides the fact that it comes from the limit as n goes to infinity of the sigma I equals 1 to n of f of, but in this case it would be 3 of, focus, 1 plus, what do I have, 2 over n squared plus 3 times 2 over n. That's literally what I use for every single one. I got my 2 over by my distance between. Pause. Besides the fact that this, pause, makes this, check it. By the fundamental theorem of calculus that you have not seen, you have not made it forever, and I have not even shown you. Let's see if you guys can see where this 32 comes from. From a simple, ooh. Can't let the people on the side miss it. What have I just done? Oh, come on! What have I just done? Still love you though. What'd I just do? I integrated. They're easy ones, like number 1 on the quiz, and some of us got a little wrong, but it's okay.
No.
What does this mean? Did some of you already figure it out?
There's no pussy.
Did some of you figure it out?
What does it do? It's actually like what's that? Sheesh. 32.
If you plug in that guy, minus, big fat minus, plug in that guy. 27 plus 9 is 36. 36 minus 4 is... You have just seen your first definite integral solved by hand. The connection between an infinite sum and a singular subtraction of 2 antiderivatives. Oh, Danielle's like, peace, I'm gone. What did we just find? We just found section 4.3 that definite integrals are the answer to the area problem. Now, why it is, how it is, you haven't seen that. All you've seen is that it is the answer to the area question. Not in 4.2, but yes in 4.3. In 4.2, you should be able to draw it and like make a triangle or make a semicircle. If it says like geometry. Otherwise, you're using the rectangle method because it's asking for the approximate answer. The exact answer will not be right. And that's getting ready for the AP too. If they say approximate, they want the approximate method. Just remember, we're being given easy functions that can be integrated. There are functions that are impossible to integrate without technology, and the technology is coded with the approximation methods going to like 1,000, 10,000, a million. You know what I mean? So it's kind of just like, remember, we're only seeing a very small subset of like, I can do this by hand, but get a complicated model, you would need much more complicated methods, of which you've been introduced to with the approximation. So, guys, this is like the huge summary of everything to do with area. This guy will solve it. Technically, you haven't been taught why what I just did works, but it does. You haven't been taught why what I just did works, but it does. It's called the fundamental theorem of calculus. Don't worry, it'll be a forever card. You'll have your time with it. Hezekiah is very worried.
Sorry.
But The area problem says you're trying to find the area between a function and the x-axis between a beginning and an ending. These little bounds, what we call them, are the beginning and the ending of the area region. If they give us something like this and they say use geometry, that is exactly what you're practicing in 4.2. There's some geometric triangle or trapezoid or rectangle or semicircle that somehow defines this region. Maybe that's our warm-up next time. Seeing what you guys have gotten from section 4.2. But then if we want to approximate, we have to split it up into rectangular regions and use this idea of add together all the different bases times heights. And so section 4.3 is the bridge. Section 4.3 is the, hey, you've done this 4.2 area stuff, but we have these definite integrals that are basically where we're going to be camping out for the rest of the semester. How do they connect? And then let's move on with the integral. 4.3 is what's really making that connection clear. And if you guys notice, there are 20 slides on this dude. Thankfully, we have Thursday, and Thursday is going to be our 4.3 workday. But I wanted you to see that 4.3 is like, hey, come here, area. Let me take you to infinity. And I do that with an integral. There are going to be a couple other, like, Riemann sum things that we're going to talk about. Trapezoids come in because technically it is another method, but it uses a different geometry formula. So we're going to see that next time. But I'm going to let you guys do 4.2 homework first so you get the rectangles down really well. But after you get the rectangles down really well, this is going to be a forever card to say, hey, you can use rectangles. That's what you're going to be practicing in 4.2. You can also technically use trapezoids only if they ask it. Because the crazy thing that I just showed you in 4.2 is actually, I don't need a great midpoint approximation. I'm just taking from the right because it's easiest to write in a formula. You're like, that's easy. It is. This is the easiest one to put into a formula. Because I get to start one away from A, which makes everything a lot easier with my bounds and everything. But I don't need a snazzy trapezoid. I don't need a snazzy midpoint. It's great for like a finite approximation. It's cruddy for trying to actually put in an infinite sum. So this is great and all. If they ask us, we'll know how to do it. But this is the forever card for section 4.2. This is where I'm ending today. Because on Thursday we'll say, how did 4.2 go? As we build on trapezoids. As we build on trapezoids to give us one last approximation experience. And the forever card. And then we say, oh, but we're going to infinity now. Oh! Look at this guy. The question, ew. Sorry. Don't look. That's nasty.
Cover your eyes.
Okay, you can look again. It was like off center. I don't know why. There you go. Next time we get to go infinity, but we're not just going to go to infinity. We're going to actually just go straight to the definite integral and have fun with it. What's the deadline on homework, cool kids? Tonight, right?